Hello everyone and welcome back to the Game Engine Development Series. In this third episode, we will see how to initialize our game engine. In particular, we will see what is and how to create the game engine interface, how to implement the game engine interface concretely by creating the so-called concrete class, and in the end, we will see how to provide a suitable function to the user in order to initialize our engine. Very well, let's start by recapping the requirements. The name of our project is Ground Engine. The purpose of the project is to provide a game engine framework for the 3D game development at low level. For this project, we use C++ as programming language and, where possible, features of the modern C++. The target platforms of our game engine are Windows initially and macOS and Linux later. Very well, at this point we can go ahead with the design of our game engine. As usual, we are going to use the UML language and StarUML tool. The last time we have created the GApplication class, an entry point class that allows the client, that is the user developer of the library, to integrate Ground Engine with his/her own application. For now, GApplication is only an empty class that does basic stuff, like providing the main loop when the client calls the run method. But today we want to finally create and integrate the game engine class. Let's start by renaming the Ground Engine package with Ground in order to simplify a bit the naming. And now let's add a further package inside Ground called Engine. This package allows to separate the core classes of the engine from other classes of the library. Now, what do we have to do? Let's add a new class in the engine package and let's call it Ground Engine. Before to go ahead, let's think about how we can design such class. In general, when we have to design a library, we have to think about two distinct areas: the API of the library and the classes that concretely implement it. API stands for Application Program Interface, and as the name suggests, it's a set of one or more classes provided to the client to control and manage one or more software systems, in our case, a game engine. An API can be composed by many types of classes. In our game engine, we will deal mainly with inheritable classes, like our GApplication class, and the interfaces. An interface is a pure abstract class that provides only the signature of its methods, but not their implementation. For example, the Ground Engine class we have just created is a really good candidate to be an interface. In StarUML, in order to define a class as an interface, we have to set the attribute isAbstract. The task to provide implementation to the methods of an interface is relegated instead to the so-called concrete classes. In our case, we can create another class called CEngine, that stands for Concrete Engine, that is the concrete class of the Ground Engine interface. In order to implement concretely the methods of an interface, a concrete class must derive from that interface. So let's derive CEngine from Ground Engine. Good! What happens now? As we have said previously, the design of our library is subdivided in two main areas: API and concrete classes. Only the API will be provided to the client, that is generally placed in a public folder like include. The concrete classes, instead, will be hidden inside the library and are generally placed in a private folder like source. Very well. Now that we know generally what is an API and what's the difference between interface and concrete classes, Let's start to design the ground engine classes and how the client of the library can initialize and use them. In this moment, we want to allow the user to create and retrieve an instance of ground engine. This involves the instantiation of the CEngine class. The problem is that we don't want to expose the concrete class to the external. A common way to solve this problem is to provide a public global function to the user that we can call createGroundEngine that returns a pointer of type GroundEngine interface. Unfortunately, there is no standard way to define global functions in UML, so one option is to create a further class called createGroundEngine. And set global function as a stereotype. In the end, we add a method, again createGroundEngine, where we define in detail the function. Then, inside the createGroundEngine function implementation, we will instantiate concretely and privately the CEngine class. In this way, the client externally is allowed only to call createGroundEngine function in order to create, initialize, and get the pointer to GroundEngine interface. Good! Unfortunately, there are a lot of other things to take care of. First of all, do we want to allow the client to create more than one instance of our engine during the execution of our program? Usually, a so big software system like a game engine should be instantiated once during the lifetime of a program. This because our engine in the future will deal with many other internal software subsystems like graphics engine, physics engine, and so on. And the set of all these systems is surely heavy to handle repeatedly. Not to mention that some of these subsystems, in turn, don't allow to create more than one instance. That's why we should constrain the user to create only one instance of our engine. So, in order to have only one instance of our engine, we have to design our CEngine class in a specific way. In particular, we should use the so-called static factory method. A static factory method allows to create instances of a specific class by using a static method like createInstance. So let's add a static method called create in our CEngine class. To define a static method in *UML, we have to select the method and set the isStatic attribute. So, in the static factory method just created, we should create one single instance of CEngine class and store it in a static attribute called instance of type CEngine pointer. Classes like CEngine are also referred as instance-controlled classes because they control how many instances can be created. In particular, CEngine class will be of type non-instantiable, and so we will allow its instantiation only in the create method and stop. Then we have to create even a static destroy method, whose purpose is to handle the deallocation of the CEngine instance stored previously. Very well, at this point we should allow the client to release the engine. The release of an object should be handled automatically through the usage of smart pointers that we will face in the next tutorials. For now, let's add a pure virtual method called release in GroundEngine interface. To define a pure abstract method, we have to set the isAbstract attribute. At the end, let's implement the release method in CEngine. So far, so good. We have finished to design the very first classes of our engine. One last thing to do is to exploit our GApplication class to initialize and release the engine for us. So let's add two dependencies to GApplication class, one to the createGroundEngine global function, because we will use it to create the GroundEngine instance, and another one to the GroundEngine interface. let's add a new pointer of type runEngine in order to store the engine instance. Finally, let's add a last method in GApplication called onUpdate, a callback method that will be called at each iteration of the main loop. This method will allow us to place logic inside the loop. That's all. We have gathered all the necessary information to start the implementation. As first thing, let's open the include folder and let's rename the ground engine folder in ground. At this point, let's add a new folder in source folder and let's call it again ground. Let's move the application folder inside it. Now we have to fix all the ground include paths in the various header and C++ files. Very well, let's go to gapplication C++ file. Here in the constructor, in order to have only one instance of gapplication, we throw an exception when a further instance is created. The problem is that an exception should be used to signal an error when a function couldn't do what it advertised. In our case, if we have more than one instance, we want to stop the execution of our program. In order to do that, let's go to gcommon header file and in the ground Windows definition, let's define a new macro called gassert. The purpose of this macro is to abort the application if a particular condition is not satisfied. Let's add two brackets that allow us to put a semicolon when we use it in our code. In order to create a multi-line macro, we have to place backslashes at the end of each line. At this point, if the condition is false, then we call the abort function that terminates the program. Don't add the back break here, that is not suitable for this case. Good. In G application C++ file, let's remove all the code related to the exception and let's use the gassert macro. Here we assert that we don't have any instance. If this condition is not true, the program will be aborted. Let's do the same thing even for the get function. Now we can finally implement our engine, so let's add a new folder in include and let's call it engine. Here let's add a new header file and let's call it ground engine. As first thing, let's add the ground namespace and let's add the ground engine class. As we have already seen in the design part, ground engine should be an interface, a pure abstract class. To do that, we have to add and implement the constructor and destructor methods, and in the end we have to add a pure virtual method called release. We can define a virtual method pure and so without implementation by adding the equals 0 at the end of the method signature. Very well. At this point, let's add the engine folder and let's create the CEngine concrete class. Now we have to inherit from ground engine interface. Let's start to implement the class. Let's make the constructor and destructor private. In such a way, we are not able to instantiate the class directly. Then let's override the virtual method release of ground engine interface. In the end, let's define the static factory method called create. Let's define also the destroy method as a private method. The allocation should be handled only through the public release method. Finally, let's add the static attribute instance. So far so good, let's implement all these methods. In C++ file, let's initialize the static attribute as null pointer. Let's start to implement the create method by adding the assert method. The precondition of this method is to have a null pointer instance. If the execution proceeds, let's create the cng instance through the new function. The destroy method is similar, with the difference that the precondition is to have an instance of cng class, and in that case we simply delete it. At this point, let's go to ground engine header file and let's add the create ground engine global function. The global function symbol must be exported in order to be used by the client. Very well, we place the implementation of create ground engine function inside the cengine C++ file. And here we simply call the static factory method create. Once we want to release the instance of our engine, we call the static destroy method. Good, let's move on and let's handle ground engine inside GApplication class. So let's add a new attribute engine of type ground engine pointer. During the GApplication constructor, let's create the engine through the create ground engine global function. And let's release the engine during the GApplication destructor. Consider that the release method should not be called manually by the user, but through smart pointers that we will face in the next tutorials. Very well, let's start to compile our engine. It works, now let's debug it. Let's place a breakpoint here. Here we check if the instance attribute is currently a null pointer. In this case, let's press F10, then we place the current instance in the instance attribute, and in the end, we can finally create our ground engine. Here let's press F11. At this point we call the create method, and if we don't have an instance of this class, let's allocate the first one and let's return it. Good, if we go ahead, we arrive to the main loop, from which we cannot escape. Let's start to give a bit of control to the client over the main loop by adding the onUpdate method in GApplication class. Let's call onUpdate inside the loop. In the end, let's override onUpdate method in the example application class of the client. In the onUpdate method, let's test the quit method. Let's move the breakpoint in correspondence of app run. Let's debug our app. When we reach the quit method, the isRunning flag is set to false, in such a way to break the loop and close the app. Let's put a breakpoint when we release the engine. When we exit from the loop, the run method terminates and we return for the main function. During this step, the scope of example application object terminates and the destructor method is called. At this point, we release our engine by calling the static destroy method. So far so good. One last thing to do is to reset the instance pointer once the instance has been deleted. This will allow us to recreate another instance of our engine. The most important thing is to not allow the client to create more than one instance at a time. Let's do some tests. Let's create another instance of example application and let's see what happens. If one instance of this class has been already created, the hazard aborts the app in that specific point. Let's do another test for the static get method. If we haven't created a GApplication instance yet, the app will be aborted as well. That's all for now, folks. Today we have seen how to initialize our game engine. I hope you enjoyed this video tutorial. See you soon. Thanks for watching.